Hey there, Math 126 fans. This is going to be part one. Just in a few general comments I thought before I launched into bigger things. But really, all of chapter 14 and 15, which is what exam 2 is typically about in Math 126, is about learning to work with multivariable functions. This is different than what you were doing when you were studying curves. This tends to lead to things called surfaces. And what we're saying is, you have some surface. Let me make my head a little smaller. My darn big fat head is always in the way. We've got some flying carpet here. That's how I always draw surfaces. I tell students I don't try to make accurate drawings anymore. I just need to attach my brain to something. We give you a point X, Y on the ground. You plug it in, that gives you a Z, and that's this height. So that's what we're working with. Now, actually generating a 3D model is good for some things, but honestly, it's not really good for many things. Like if you're going for a hike, you don't want to do that. So at the beginning of chapter 14, you talked in general. There's not that many questions we can ask. It would be good to review the 14.1 homework. But, I mean, for whatever my complaints might be about the competitiveness of UW, UW is gorgeous when it's not raining. But anyways, there's Mount Rainier. And if I had to go for a hike on Mount Rainier, I'd probably not survive because I'm so out of shape. But I wouldn't want to carry around a 3D model of it. So how do we navigate it? We navigate it with a map, a contour map, an elevation map. And that's often something students get confused about, but in my opinion, it's the best visual of something like this. And so you learned a little bit about how to make such things. So I wanted to say a few comments about that. I grabbed this from the... this is a free downloadable PDF of a map of Mount Rainier. Thank you for State of Washington for making that. So you can see what they've done. They've labeled various heights. I think that's in feet, 13,000 feet. And you can see various things. So if you are someone who's gone for hikes, you sort of know that if these are equally spaced contours, there's a big difference between what's happening like here and what's happening here. Think for a second, where is it steeper? Here, when you walk from there to there, each one of these lines represents, 100 feet. Maybe I'm off. But let's say it represents 100 feet. Here you go up 500 feet in that span of space. Here you go up 100 feet. This is much steeper. Again, you don't really need to know that, but I like to always say this to students when we're doing this, we first sing this in class. What we're going to do in Math 126 is say, what if you're standing at some random point here and you have to figure out the slope this way and the slope this way? That's what you're doing when you're doing the partial derivatives. You're defining a set of axes. Maybe this is x, maybe this is y. You're looking down from above, and we're going to compute the slope in the x direction and the slope in the y direction. And the truth is, there are many other directions. Those are called directional derivatives, and we don't study those in Math 126. You got to take Math 224 to study those. The steepest direction is called the gradient. We don't study that either. It turns out you can do a lot of stuff with just these two slopes. In fact, if you're at the peak, the slope in both directions is 0. So that's some of the big ideas. I just like to say that now before we move on. But you can see like steep here, less steep here. Okay, so it's just a little bit about reading a contour map. Because honestly, if you had to study a shape and there's no good calculus way to do it, you would want to generate a contour map. Okay, a few general things, all I could think of in terms of asking questions. One question that I get a lot that came up in the homework is domain. There's something about this domain question that scares people. I've never figured that out. Domain questions should never be hard. I think the issue is, I should say, domain question, the type of domain questions you would be asked in an algebra or calculus class shouldn't be hard. They do require you know your functions and where they have trouble. So this is just a general comment. Sometimes I find by not making it an x, it helps students. So when I have a function, and I'm always surprised when people don't know this, so just quickly, if I said graph the function for square root of 4 minus x, some people would know how to shift or whatever, but one of the first things you could do is you could ask the domain. This only makes sense if the thing under the radical, the blah, in this case the blah is 4 minus x is greater than or equal to 0. So we need 4 minus x is greater than or equal to 0. That means 4 is greater than or equal to x. And in 2D, when you go to graph that, it's just a region. You say, I want to shade all the x's greater than 4. And the graph is only going to be there. People watching this video are like, he's already made a mistake. We all make mistakes. X is less than or equal to 4. I wrote it. Okay, so when you go to graph it, it actually looks like this. It's almost like if you were to shine a light from above, what's the shadow? But that's the domain. So why are we asking this question here? Because the domain becomes something a little different when you get to 3D. Because when you get to 3D, it's a region on the ground. And to me, that's the number one difference between 2D and 3D, is now we have to think about regions. Darn head in the way again. Let's make it really small. Okay, so these questions are just asking that. So when someone says, what's the domain of log of y minus x, you go, oh yeah, I know that log only makes sense if this thing is bigger than 0, which means y has to be bigger than x, which means in 2D, you should draw y equals x. This is how I tell students to do it if you don't know. The fact that it's strictly greater than, put a little dotted line, and then if you don't know how to see it, check a number on each side. Let's try 0, 4. Does 0, 4 work? When this is 0, is 4 bigger? Yes, you shade this side. Now that might seem weird, but what that is saying is if I go to graph this in 3D, I only need to look above that. And some students go, well, I just cannot think in 3D. So that's why when I teach the course, I make lots of visuals. You don't have to have visuals, but that's the graph of that surface. Now, it has trouble graphing it because there's these asymptotes. But if you look at it from above, notice it's only the stuff that's up there. You might be confused by orientation. You know, it always depends on what I'm calling y and x, but that's that region I was talking about. Okay, what about the next one? This only makes sense if y plus x squared is greater than or equal to 0. So y has to be greater than or equal to negative x squared. What does negative x squared look like? It's a parabola. So the reason you had questions like this is to, and I'm spending too much time here, but I want to make sure our beginnings are good. If you want to skip ahead to the other videos, you can. I just wanted to hit these topics before we go. So it's only going to be above here. So actually, since this is the y-axis, it's going to be like over here. And it's only going to make sense out here. Those are the only points you can plug into that. Say, well, that's hard for me to understand. So again, if you take Math 126 from me, you're going to get lots of visuals. Here's the surface. I'm expecting that it only is going to make sense above that parabola. Boom, baby. There it is. Oh, it did a little choppy because I graphed too far out. Sampling problem. Okay, that makes it look a little better. So whatever the shape is, that's not what I'm asking. The question is just saying, do you realize you can't plug anything down here? So I feel like that gives a better feel for what's going on there. Okay, we'll finish this with a big discussion of traces. So I showed you the contour map, the elevation map, the level curves. Unfortunately, I have a lot of names for this because these are really important in general when you're studying 3D objects. How do we generate that? Okay, so let's look at one example, and then we'll find one old question. So here's a function that I always use in my class, just a relatively quick one. Those of you that have taken Math 126 and done 12.6, you actually know the name of this. This is a paraboloid. It's a circular paraboloid. If you were to graph it in 3D, I'll show you this here. Looks like this. I used polar, that's beside the point. I wanted to make it look nice. It takes some work to make things look nice in 3D, but there it is. That's z equals 9. I chopped it off at 0. It keeps going if I go further. That's it. What if I wanted to play around with that? The actual function just tells me this height. So this is this height everywhere. If you can see it. That's what the function does. So there are 3 coordinates, but x and y are the input. So as I can see it, if I just want to talk about the positive, the domain would be that circle. All right. If I wanted to make this a 2D level curve graph, I just look at different levels, some equally spaced levels. And that's actually really easy to do. You just say, okay, 9 appears to be the top. So what happens when this equals 9? What happens when this equals, 6? What happens when this equals 3? What happens when this equals 0? You set those equal and you solve. Basically, and then you can graph. Those are your level curves. So you would figure out what that is. You'd figure out what this is. You'd figure out what this is. Now, if you're just trying to get a sense, you should realize those are all circles. This is a circle of radius 3. This is a circle of radius square root of 6. This is a circle of radius square root of 3. This is a circle of radius 0, or just a point. So I'm going to graph those. Let's take a look. So these are really important ideas. It's just hard for us to ask about this on a test. So I thought I should start with this. So here's those level curves. That's the circle of radius 3. That corresponds to when we're at sea level, when we're at the ground. That's that level curve. Boom. Level curve at here. This is when you're 3 units up. Let's go to 3 units up. Here's 3 units up. I can't hit it. Close enough. Here is, if you actually were looking at it up there, here is it hitting it. Oh yeah, I love making these visuals. As you can see, take calculus with me. I've taught this so much that I have so much stuff. There it is. The visuals aren't necessary to do the problem, but they're fun. Here I'll show you both. Let's watch the level curves being drawn. So here I'm drawing the corresponding level curve below as we go up. And what do I mean, the corresponding level curve? Here, you can see it on the ground. Those are the level curves. Cool? There they are. Boom. So when you're making a contour map, like when the people at the national parks made this, they had to make a choice to space it every 100. That's the map maker's choice. Okay? So we like to use equally spaced points so that we can make various conclusions about it. All right, that's more than you need. I just find that students think of level curves as something scarier than it is. We're really just chopping it off and then drawing the corresponding thing, but we're drawing it on the ground. And to me, once we've done that, I don't need the surface anymore. I can look at this to analyze it. It's nice to label that, like labeling that dot 9, labeling this dot 6, labeling this circle. This is not a dot, it's a circle. Circle 6, circle 3 through circle. And then you can say things like, okay, if I walk along the surface from x equals 3 to x equals 0, I'm going to be going uphill. If I walk down this, I'm going to be going downhill. So with practice, looking at that is helpful. Okay, I only could find one exam question that was on this by a different instructor. I typically only use my exams. Hopefully this instructor will forgive me. I just wanted to have one. So this is a kind of an open-ended question. Can you find something, z equals something, that would have these level curves? Now it's very open. Oh, it says it's parabolas. So what I would try to do is to think about what sort of parabolas are those. They're parabolas that are turned to the right. So in my head, I'd be thinking, those kind of look like x equals y squared. In fact, that's what this one probably is. The other ones just look like they're shifted from that. So maybe you have x equals y squared plus 1. And maybe you have x equals y squared plus 2, or x equals y squared. So that was the main thing you had to see. Now, how could I put that in a form so it's z equals something, and when you replace z with a 1 or a 2 or a 3, you get this? So that was the main observation you had to make, was to rearrange this. And so you can write it either way, but how about x minus y squared? So what if this? So it was kind of an open-ended question somewhat. But now what happens? If I replace z with 0, I get exactly this. If I replace z with 1, I actually get a negative 1, but that's fine. If I put z with 2, so that's what the whoever wrote this question was after. There's a lot of other correct answers. Okay. I think I'll leave it at that. I hope that was interesting. I should stop now because I think that's already way too long. But now I'll get into the actual problems. I just wanted to set this